This is our third session on NMR, and we're going to have a look today at chemical shift in proton NMR. I'm just going to remind ourselves about a few key ideas and key words that we're going to come across today, some of which we're going to use and some we aren't. First of all is the idea of chemical shift. We spoke about that last time. It's measured in parts per million. Often it has the symbol lowercase delta, and it gives us an indication of the environment that the hydrogen atom is in. We spoke last time about the effect of electronegative atoms. If we have a look at a really straightforward compound, so if we have a look at this compound, which is propane, then if we were to run an NMR spectrum of this, hopefully we recognise that this environment and this environment are equivalent to each other, and we've only really got two environments, that environment there and this one here, but they're all very shielded. There's no electronegative atoms attached to it, so in terms of where we're expecting to see this on our spectrum, remember our spectrum starts at 0 ppm on the right, and the further to the left we are, the more de-shielded the proton is. We would expect these to be right up here, very close to 0. If we have a look at a similar compound but that has an electronegative atom in it, for example this one here, then we've still got two proton environments, this environment and this environment equivalent to each other, and then we've got this environment here, we'll call this A and this B. We would expect to see this environment much further downfield, de-shielded. The reason being, it's attached to a carbon atom that's attached to a electronegative atom. So the chlorine is pulling electron density off of this carbon and therefore this hydrogen, making this de-shielded. And these CH3 groups, these methyl groups, would be to some extent affected by the presence of that chlorine, nowhere near as much as this one, so it would be shifted a little bit further downfield. We also spoke about integral. Integral is simply the number of hydrogen atoms in a particular environment. It's often the simplest ratio, and we'll see those on example 2 when I have a look through them. And then also we get the splitting pattern. We're not going to deal with the splitting pattern in this video. If you have a look at the AQA data sheet, so if you search for AQA A-level chemistry and have a look at their data sheet on page 3, you will find this data sheet, and this tells us where we're expecting to see certain hydrogens. So if you look at the example I spoke about earlier, was where we had a carbon that was attached to a chlorine. The hydrogens attached to that carbon are going to be quite de-shielded. Something to point out on here as well is that the hydrogens in a alcohol, they have a very, very big range. You can find them in almost half of the spectrum. So let's have a look at some real examples. So this is an example that we saw when we had a look at carbon NMR, and now we're going to use it for the hydrogen or proton NMR. We recognised last time that this is there's some symmetry involved in that structure, which means that there is some equivalent hydrogen atoms. So if we have a look at each carbon atom here, this carbon atom has got 3 hydrogen atoms attached to it. This carbon atom here has got 1 hydrogen, and this one here has got 2 hydrogen atoms. But we know that this is equivalent to that, that is equivalent to that, and that is equivalent to that. So there is some symmetry there. So if I was going to label each of my 3 environments, I would label that as the red environment, or environment A. This is environment B, and then these 2 as environment C. just looking at this spectrum, we could make a really good prediction early on about where we would expect to see this compared to these two. This hydrogen is attached to a carbon that's attached to an electronegative atom, the chlorine atom, so we're expecting to see this quite de-shielded. We're expecting to see it quite far down field. So it'll be a very, very good prediction to say that that is environment B. And if we have a look at our data sheet, in fact that is correct. So the hydrogen there, which is attached to the carbon, which is attached to a chlorine, we expect to see between 3.1 and 4.2, which is that range there. So that was a good guess. For environments A and C, for the moment we're not going to worry about how we'd resolve these and work out which one is which. We'll do that when we have a look at splitting, but we're going to expect to see them, environments A and C are going to be these two here. Let's have a look at example number 2. So again, this was some example that we saw with carbon NMR. Hopefully we recognised or remember that there is an axis of rotation around this nitrogen atom. That means that the hydrogens attached to here and here are equivalent to each other. So if we draw these out, then it's fair to say that all of these can be labelled as environment A. There's obviously no hydrogens on there, no hydrogens on there, which means that there's only one other hydrogen environment, which is this one here, which we'll call environment B. If we have a look at the number of hydrogens in each, environment A is a 6 hydrogen environment, environment B is a 3 hydrogen environment, and we're given the integrals in here, but we're given integrals of 2 and 1. The simplest whole number ratio of 6 to 3 is going to be 2 to 1, so that is as we expect. So without even looking at the chemical shift, we could identify this peak as belonging to environment A and this peak as belonging to environment B. But let's check it with our chemical shift. So environment A is just probably about 2.1, 2.2 ppm. If we have a look at where we expect to see this, this is probably going to be our best example here. We've got a carbonyl group here, carbonyl group here, carbon, carbon, hydrogen, hydrogen. 2.1 to 2.6, that is exactly where we expect to find it. As far as the other examples concerned, actually as far as AQA is concerned, we don't need to know about hydrogens on methyl groups attached to nitrogens, so we don't actually know where we're expecting to see that, but it's a reasonable assumption to assume it's going to be a little bit more de-shielded, because the nitrogen atom on here is going to be pulling a little bit of electron density off of here. Let's have a look at example 3. Now it may be from now on that you want to pause the video and have a go at doing these yourselves, in which case do that, and then we can obviously stop, and then I'm going to go through them for you. So looking at this example, I'm going to label the hydrogens on here as environment A. So we've got 6 hydrogens in this environment. I'm going to label the single hydrogen that's going to be attached to this carbon atom as environment B, and I'm going to label the 3 hydrogens on here as environment C. So in terms of integral, 6 hydrogen environment is going to be that one, the 3 hydrogen environment that one, and the 1 hydrogen environment that one. Let's check it in terms of chemical shift. So in the 6 hydrogen environment, which is environment A, is very much one of the CH3 environments that's attached to an R group, which we expect to see between 0.7 and 1.2. It's not far off of there. Let's shift it up a little bit, so that's about 1.3, 1.4, but that's going to be due to the effect of the oxygen there. Our environment C here is again likely to be one as a result, next to an oxygen, carbon next to an oxygen there, so 3.1 to 3.9 is a little bit out of the range, but it's not a bad fit, and we can definitely identify it as a result of the hydrogen, and as a result of the carbonyl group there. And our final environment, the environment B over here, that is definitely within the range of 3.7 to 4.1, which is as we expect on here. Environment 4, example number 4, we've got 3 hydrogen environments, environment A, B and C. So environment A is likely to be the most shielded environment, probably this environment here, because it's the furthest away from any electronegative or electron withdrawing groups. If we have a look at where we're expecting to see it, according to our data sheet, between 0.7 and 1.2, that's just about in range there, so that's probably about 1.3, so 0.7 to 1.2 there, so that's definitely environment A as a result of the chemical shift and also as a result of the integral. Environment B is a 2 hydrogen environment, which we can tell from the integral, and it's being de-shielded, and it's within the range of 3.7 to 4.1, which we're expecting to see there as a result of this group here. So 3.7 to 4.1, and then our final environment here, that singlet, is environment C, and that again is within the range that we're going to expect here of 2.1 to 2.6. Question 5. So, this compound here, there are 3 hydrogen environments. There's obviously 3 hydrogens on there, and on there. They're all equivalent to each other. Because of this axis of rotation around here, these are equivalent environments, so this would be a 9 hydrogen environment. There's obviously no hydrogen on here. There's going to be 2 hydrogens on here, which is environment B, and then environment C is this one here. This one's a nice straightforward one for us to sort out using chemical shift. 9H environment, these CH3 groups are a long way away from any electron withdrawing groups, so they're going to be quite shielded, so they're going to be quite shifted up here. That's likely to be our CH3 groups, which is 0.7 to 1.2, which is within the range, just about within the range that we'd expect. Environment B, this hydrogen environment here, we're going to expect to see this peak between about 2.1 and 2.6 because it's next to the carbonyl here. So that is indeed correct according to the chemical shift. And then this incredibly de-shielded, very acidic proton, you can just about see as a little lump there, and that is in fact in the correct range of 10.0 to 12.0, which is where we expect to see the acidic hydrogen. So we'll call this A, this B, and this C. Question 6. Again, quite a straightforward spectrum. If we just predict before we even jump straight in, I'm going to draw the hydrogens in now because I haven't done that for a while. So we've got some symmetry here, so all of these hydrogens are equivalent to each other, and we'll call that environment A, and then this is environment B. So just looking at making a prediction about it, we're going to expect to see this hydrogen quite deshielded, moved quite far downfield. So if we have a look at that, we're expecting to see this between 3.1 and 4.2, which it indeed is. So that's environment B. And then if we look at this one, these are CH3 groups, but don't forget that they are being deshielded to some extent by the electron withdrawing effect of that chlorine there, but that is within the range of 0.7 and 1 point just about that we're expecting to see it in. Question 7. So question 7, let's start by looking at the hydrogen environment. We'll call this environment A. It's a 2 hydrogen environment. There's obviously no hydrogens on there, so then we'll call this environment B, which is a 1 hydrogen environment. The easiest one to assign is going to be this proton here. Environment B, it's a acidic OH, which we expect between 10.0 and 12.0, and absolutely it is within the range of 10.0 and 12.0. And then again we've got the hydrogen that's attached to a carbon, attached to a chlorine, between 3.1 and 4.2, which is just about in range there, 3.1 and 4.2. And the 8th and final example. So let's label the hydrogen environment. Environment A, environment B, which is a 2 hydrogen environment, and just remember that is also a 3 hydrogen environment, and then environment C, which is a 1 hydrogen environment. Let's start with environment C. It's probably the more likely easier one for us to assign. It's the acidic hydrogen again on the carboxylic acid within the range 10.0 and 12.0, exactly where we expect to see it. For these two here, we could use the splitting pattern to identify them, but we can also do it based on chemical shift. Environment B is likely to be this one, due to the fact it's shifted between 2.1 and 2.6 here, so that group there. And that means that environment A is going to be this one here. We would reasonably expect it to be one of these ones here, but it will have been shifted downfield to some extent by the electron withdrawing nature of the carboxylic acid group there. So we expect to see it between 0.7 and 1.2, and we just about see it at 1.2. Okay, thank you very much.